Hello and welcome to this lecture. In this very brief lecture, I'm going to show you cases where the examples that we saw where it was not diagonalizable and what people typically do in that case. Okay, so this is not really diagonalizability, and you can consider this sort of like out of syllabus a little bit, but nevertheless, it's an interesting thing for you to do in case you cannot do diagonalization. What next, right? So that's the thing. So let's see some examples. So here is the example that we saw, this 1, 1, 3 example where you had only 2 independent eigenvectors. Okay. So the third independent vector is not there. So this ends up being non-diagonalizable. So what's the best we can do? You cannot diagonalize this one, but can I make it nearly diagonal? Okay, so that's the next question. So for that, here is a trick. Okay, so this trick I'm not going to explain in great detail, but I'm going to just show you the answer just to show you that what is possible. So what people do in this case is they take these eigenvectors, and you know that if you have 2 vectors, you can always extend, right? We saw how 2 vectors can be extended to form a, come up with a third vector and create a basis, right? So that's what is typically done. So this V0 is not an eigenvector, okay? So I'm not listing it under eigenvectors. Eigenvectors are from the right here. So 1 and 3 are eigenvectors. There's an X here. So this is not an eigenvector, but it is linearly independent from V1 and V2, and together they form a basis, okay? So I've picked this V0 very carefully. I could have picked 1, 0, 0, right? If you wanted a linearly independent guy, I could have picked 1, 0, 0. I've picked it very carefully. I put -2 here, I've picked 3 here. This ratio and this choice is very important. I've done it very, in some way so that I will get a nice matrix in the representation. So now if you do a matrix for T in the basis V0, V1, V2, you get something like that. You get 1, 1, 3 on the diagonal, and you get only a single 1 in the off diagonal. Everything else is 0. So in fact, this is the closest you can possibly get to a diagonal matrix, isn't it? Okay, so it's almost diagonal except one value, which is 1. All right. So this is the closest you can come to a diagonal matrix, and that is that's nice to see. And then this came about because I picked -2, 3. Okay, otherwise it wouldn't have come. -2, 3, 0. It's very important. So that way this would work. So now you can again do some sort of a similarity transformation with this S, except this D will become D tilde. It will not be D. It will be this 1, 1, 0. So you can see why, right? So it's quite reasonable. The coordinates of A V0, A times V0, the first column here, are going to be V0 times 1 plus, right? It's 1, 1, 0 in the V1, V0, V1, V2 basis, plus 1 times this second column, isn't it? Right? So that's why you get a 1, 1, 0. Previously it was all eigenvectors, so you got only in the diagonal. Now this new guy -2, 3, 0 is actually in this basis, it's 1, 1, 0. So it's a linear combination of these 2 guys, and you get that. Okay, so again you get a sort of a change of basis here, and you have these kind of formulas holding, but you don't have a diagonal matrix. Now the same thing can be repeated for the other cases also. Once again, I'm not going to go into the details. This case where we could not find 2 eigenvectors for 2, you can again extend it. In this particular case, it ends up being 1, 0, 0, simple enough extension, and you get a closest to diagonal sort of thing, 2, 1, 2, 1. Okay, so again you get this D tilde picture with non-diagonal entry here. Okay, so the last one is AAA. So let me just give you how this happens. So in this particular case, if you assume B is not 0, okay, I'm going to assume B is not 0, then you have only one eigenvector, right? So this, when you do the subtraction of A, you get rank 2, which means nullity is only 1, you get only one vector, okay? So here you have to do a very special sort of extension, and because B is not 0, you can divide by B, so you get 1 by B, C by B square, 1 by B square, etc. So if you do that, this sort of extends to a basis of R3, and then you will get A, 1, 1, and this is the closest you can get, right? So why do we get 2 1s here? Because there were 2 eigenvectors that were deficient. Anytime, how many ever repetitions you have, if you have eigenvectors being deficient, then you will get that many ones on the diagonal. You can't avoid it. Again, you can do the same sort of D tilde formulation, and you will get this picture here. Okay, so this hopefully sort of conveyed to you what to do if you cannot diagonalize. Okay, so if you can diagonalize, it's great. If you cannot diagonalize, you can always, in fact this is true, you can always get to a closest representation to the diagonal. Okay, thank you very much.